What's going on, guys? It's the Unhinged Engineer here, and I'm back today with episode 30 of my GT OMSCS vlog. And today I'm going to be talking about the second project of CS6475, which is computational photography. And the project to which I'm referring is the seam carving project. So this was the final project we had to do. It was worth 15% of our overall grade. Touched on a lot of different topics from throughout the course, as well as some new ones that we hadn't really been assessed on directly yet. And yeah, I'm excited to share what that project was like with you guys. I know this is a pretty late video, and that's mainly because this assignment took really long to do. So I apologize for the delay, but I wanted to wait until I'd seen this assignment through the end. I think I did pretty well. I passed pretty much almost all of the autograder test cases, and overall I think my implementation was solid and in line with what they were looking for. So yeah, without further ado, let's jump right into this project. So seam carving was effectively kind of a technique that we're using to do content-aware image resizing. So what does that mean, right? Content-aware image resizing effectively is about, like, if you've ever tried to stretch out an image in like PowerPoint or something and you see everything gets warped, it kind of looks weird. That's like the opposite of content-aware resizing. And effectively what's going on is you're resizing the entire shape, and so the proportions of things within that shape, or I should say within that image, are changing. Thus, the proportions of the content that like visually makes sense to you from the original image aren't preserved, and you get this weird like stretching, elongating, or crushing effect depending on in which directions you're resizing things. And so what we want to do when we're warping things is warp the spaces in which there isn't a lot of visual information and preserve the relative proportions of regions where there is a lot of visual information as much as possible. And the idea there is that once you've done the warping, important things like the proportions of different parts of a car, like different parts of letters, if you're doing this with text, are preserved, but the overall image is wider or taller or whatever, right? And so effectively, the way you do that is you, instead of shifting everything equally in vertical or horizontal seams, you draw these like weird seams around, I'm drawing them around my face here. You draw these weird seams and kind of push out or scrunch in along those seams. And those seams are drawn such that they kind of pass through the areas of the image with the least visual information, or as we refer to it, energy, right? And speaking of that energy, there's kind of like two papers that we're tasked with re-implementing here. One is about backwards energy and the other one's about forwards energy. They're effectively the same algorithm. It's just that forward energy kind of predicts what the effects of insertion and removal along the seam you decide will be, and then account for that change in energy while doing the overall energy calculation in the beginning of like what seams to create, right? So effectively, you're a little bit more aware of the effects of what you're doing in forward energy seam carving versus backwards energy alone, but it's the same exact idea, and I basically use like all the same functions with a couple of different additions that were necessary to meet the requirements of the algorithm. But yeah, so we had to do this for like, I want to say, how many test cases? Like 3 or 4 test cases. I have the README up here. Like 3 or 4 test cases. Okay, 4. 4 test cases, and just kind of demonstrate that our algorithm was working accordingly. One thing I did like with this assignment was that they kind of gave us like the answers, like visually what these images should look like, so we knew what we were doing made sense. And like that was much better than some of the other things, like project 1, for example, where I had to create my test cases as I went, right? So here we're kind of given like, oh, here are the results that you should roughly expect. And even though my results didn't match them exactly, like they were pretty damn close, and I knew that I was on the right track throughout. So that was really cool. But yeah, same kind of deal as always. Like you write out the code, because it's a project and on an assignment, it's a little bit less boilerplate. Although I'll say with this one, there's actually significantly more boilerplate than in project 1, right? So kind of somewhere in the middle between the first project and the rest of the assignments in terms of how much boilerplate you're given. But you have to color within those lines and color outside them a little bit in terms of tuning different things within your algorithm, and just writing helper functions that you can reuse over and over again to make your code less sloppy, which is not exactly something I really cared much about for the course of the assignment, but it's okay. So yeah, color that in, run the file that you create for the algorithm on all the test cases. They have a good runner for that. Just kind of passes everything through. You get, the results of like what your algorithm produced for 1 or maybe 2, like if you're comparing forwards versus backwards energy, or insertion versus removal, or double insertion, whatever, right? like you run it through, you get the relevant test cases, you get the diffs between your results and the results they provided you. So that was pretty cool. The paper actually asked you to speak to those differences a little bit, which was interesting. That was neat. So yeah, overall, run it through the runner, write the report about the, what caused the diffs that you saw, describe your algorithm in general, like we've been doing this entire freaking semester, describe the results of each image beyond those diffs, like, what parts of the visual content were preserved well, what weren't, stuff like that. Just pretty standard stuff in terms of this project. I'll say like a couple things here. For one, I think that this project was much heavier on the test cases than project 1 was. And by contrast, it was actually a lot lighter on the report, which I thought was interesting. So for this, you kind of just like write the algorithm, you run the code, you get a bunch of results, and you describe those results. Whereas previously, you had to do like a computational pipeline and answer a couple of qualitative questions and all these different things, which just kind of warrants really a part of this. Granted, I'll say I think that the algorithm we were asked to implement here was much harder than what we had to implement for project 1, which I'm going to be honest with you, I don't even remember what project 1 was about. What was project 1 about? Object removal, duh. Actually, object removal was pretty tough too. I don't know, I wouldn't even necessarily say that the code itself was harder than project 1 was, but I think the report for project 1 was definitely much more difficult than here. I will say with this stuff, there were a lot more test cases, because each test case in and of itself, usually you were doing like 1 or 2 methods, whether it's insertion or removal or forwards or backwards energy, whatever else, on these different images. And so like what you have to do in terms of overall testing was a higher bar here, but I think the report kind of fell flat, which I'm okay with because I'm really kind of sick of this class and want it to be over. So I was grateful that the report was not like as intense as the other ones were. But overall, I think it was pretty solid. Seam carving was interesting. I've never seen this kind of technology used before anywhere, which I thought was pretty weird. Like, I think honestly, looking at some of the methods, like especially drawing the seams out, because effectively if you imagine like water running down a windshield, like as that water droplet is pushing through kind of the, layer of water on the windshield, it's passing through like the regions of like the least energy, right? Everything, all physical processes try to take the path of least resistance, right? And so that water droplet's going down the windshield through whatever path of least resistance there is, given the water content on your windshield. And you're effectively doing that, except instead of like the thickness of that water on the windshield, I'm talking about the prevalence of information, which is referred to here as energy, which energy is really just the image gradient. So, surprise, surprise, right? We're just doing Sobel filters of everything all over again. So yeah, you're taking a gradient of this image and you're saying like, okay, based on these gradients, I'm seeing like there's a lot of, if the magnitude of that gradient vector is higher, that means that at this pixel, there's more energy than other ones. I should probably not draw a seam right through this, because if I do, things are gonna get wonky when I insert stuff in the middle or remove stuff, and you get this like wave front in the middle there, right? So like that piece of it was actually pretty interesting, and I would imagine would be useful, but I've never seen any applications of this stuff anywhere substantively on the internet. And I think overall, like, if this has been used before in the real world, I haven't actually seen it used much. And so, it's questionable to me how useful and applicable this algorithm was, but I do think it had some interesting concepts to it, which is more than some of the other assignments could be said about. So yeah, that was project 2. Overall, I think not really as bad as I anticipated. I was kind of dreading going into this project for many reasons that I will share with you in my final review of this class, so stay tuned for that. But to talk briefly about what's left here, I effectively have the final portfolio, which I actually thought was extra credit, but now I'm second guessing. I think it's just like part of the course, it's worth 1%. But effectively I have to make a PowerPoint of all the different things I've done throughout this course, which is like so obnoxious, right? Like I have to make a PowerPoint describing how awesome that this class was and, all the cool stuff I got to learn. I had the privilege of learning, like whoop-de-freaking-do, whatever. In case you can't tell, my review of this class is gonna be negative. But yeah, I have to write that final portfolio for 1% of my grade. I will spend a whopping 30 minutes on that. And then I have the final exam, which I honestly don't really plan to cram for very hard. It's open book, open notes, and quite frankly, the written assessments for this class have been pretty easy, so I'm not really worried about the final exam. But then I'll be done, and I will be free. And I will probably take a good minute to, A, recollect my thoughts and make sure that my review of this course isn't just a rage fest, and also B, make sure that my grade is finalized before I share my opinions with the World Wide Web here, which potentially could include any instructor. So yeah, gonna take a minute to kind of process how this class went and give a review of it, but I can give you a spoiler, it will not be good. So stay tuned for that if you feed off negativity and are chronically online. I hope you enjoyed vlog episode 30. I guess 30 is a big achievement. It feels like a big achievement. But yeah, this was kind of a standard routine vlog episode. So yeah, we've officially hit 30 episodes of the vlog. Thank you so much for watching. If you like this vlog content or are interested in my more general professional development content I make for other young engineers like myself who are trying to figure out how to navigate their career, navigate these different fields, aerospace engineering, computer science, hard tech, stuff like that. If you're interested in any of that content, like, comment, subscribe to the channel. Thank you so much for watching, and I'll see you next time.